Okay, so we have the recording started, and let's get started talking about quantifiers. So lots of times whenever we're making statements in math or in any other area where we might be using logic, we want to talk about lots of things, not just a single thing. And quantifiers are the primary tool that we have to talk about lots of things all at once. But before we can get to the two quantifiers later on in the section, we need to talk about some kinds of logical, I can't say proposition, logical sentences that need to be used in quantifiers, like this one, this sentence. So I'm labeling it P, and the sentence is N is an even integer. So let's think about for this for a second. Um, is P a proposition? And remember, a proposition is a sentence, whether it's in English or in mathematical symbols, that is either true or false.
It is a proposition.
Okay, so it definitely looks a lot like a proposition, but look at this character n. So n is a variable. Right, so the truth value of this sentence depends on the value of n. So we can't really say for sure that this is a proposition because we want to think of n as something where we can plug in a number. So you might plug in 1, you might plug in 2 or 3. So the answer to this question is not really. It's not really a proposition because we want to think of n as a variable, not as a constant number. So this isn't a proposition, but it is, or it certainly seems to be, a very typical kind of statement that you might make, a typical kind of sentence that you might say or write. So what is it if it's not a proposition? And that gets to the next definition. So this sentence here is an example of what I'm about to talk about. Let P of X be a sentence involving the variable X, and let D be some set. We call P a propositional function. Or sometimes predicate. You won't see this word used very much in our class, but if you looked at a book on logic, you might see it. So P is called a propositional function or predicate if for each value of X in your set, when you plug X into the sentence, you get a proposition. So this notation is like a function, like f of x equals x squared. So this is a normal function with numbers. Now we're talking about functions where we're plugging in maybe words or anything to make propositions. So plug in x and the output is a proposition. So instead of a number, we get something logical, something that's true or false. So what is D? So D is the domain. So you might remember from an algebra class or something like that, that the domain of a function is the set of things that you can plug in. And D is the set of things that we're plugging into this propositional function. And usually we use the word domain, but we say the domain of discourse when we're talking about logic. So we say discourse because we're speaking. Discourse means something like conversation or something like that. So as I said, this original sentence P is one of these propositional functions. So if I take a number, let's say 2, you might say P of 2 is the sentence 2 is an even integer. And this is a true proposition. Or if we had plugged in 3, we would get a false proposition. So what should the domain of discourse be for this propositional function P? Any ideas? What sorts of things can we plug in?
Even integers.
So if we plug in an even integer, we'll always get a true proposition. But remember, it could be false as well. So we could have odd integers. In fact, we could have any integers. So odd or even, Z. Good. Any questions so far about this definition? Okay. So propositional functions can also take the form of equations. And the thing that's being plugged into the function is the value of x. So if I take any number and put it into my equation, either this is going to be true, the left side is going to be equal to 1, or it's not going to be true, the left side is not going to be equal to 1. And since we're plugging in numbers, in fact, we can plug in any number we like here. The domain of discourse is the set of real numbers. So that was the capital R, the special capital R. That was our symbol for it. Okay, so the first two examples were mathematical. These kinds of things show up in regular conversation as well, these propositional functions. There's a grammatical error there, though. So this particular sentence, the film grossed over $100 million at the box office, depends on the value of the film. It depends on what film you're actually talking about. So if you were talking about a big blockbuster, like maybe the latest Marvel movie, this would probably be a true statement. If you were talking about some art house movie that was put together on a shoestring budget by a college student, probably not. So the domain of discourse, the things that we can plug in for the film, what should that be? Any ideas?
All films.
All films. And probably we want to say all films that were actually released in theaters. But all films is fine. This sentence wouldn't really apply to a streaming movie on Netflix or similar streaming services. Good. Okay, so questions about what we're talking about here. Okay, so now that we know what a propositional function is, we can start talking about quantifiers. Okay, so in this definition, we need to start with a propositional function, P, like what we talked about on the last page. Then this new statement that I'm about to write, for every x, P of x, is called a universally quantified statement. So universally, because we're talking about everything, that's where this word comes in, or at least everything in our domain. And what this statement is saying is that for every x, it's P of x should be true. So when you just write this by itself, you're asserting that P of x is true. Whatever this proposition turns out to be. And we'll get to some examples in just a minute. There's a little bit of notation. Instead of writing for every x, instead what we do in mathematics is use this symbol. And it's a capital A that's been turned upside down. And it simply means for every. So instead of writing out the words, what we'll write in math is the upside down A, the letter X, and then the proposition, P of X. So this is the symbolic way of writing this same sentence. And this means essentially what you think it should mean. The statement for all or for every x, P of x is true if the proposition P of x is true no matter what value of x you plug in. So for every x in D, the domain of discourse, you're just saying that this is always true no matter which particular thing x you're talking about. And the opposite of that, the negation, this is false if there's one of these values of x where this proposition is false. So it's false if P of x is false for at least one. One value of x in D, the domain of discourse. Okay, so here's our first example. I wrote this symbolically. We should also think about what this means in English, because when you see these symbols, you need to be able to translate it, at least in your mind, into what the symbols mean. And we just have to work it out. This upside down A with an X next to it, remember, means for every X. And then the propositional function is this inequality that asserts that x squared is greater than or equal to 0. So is this true? Is this quantified statement true? Or false? What do you think? Oh, and another question, what's the domain of discourse? That's important. Maybe I'll just tell you the domain. All positive real numbers. What about negative real numbers? Okay, so if x is positive, let's say if x is greater than or equal to 0, then you're saying that x squared is definitely greater than or equal to 0. That's good, right? You're multiplying a positive number by itself. And Kendrick, yes, you're right. If you have a negative number, so if your value of x is less than 0, then when you multiply a negative number by another negative number, you end up with something positive. So x squared is also greater than or equal to 0 in that case. Good. So this is a true proposition. Any questions? Oh, it doesn't seem like we have any questions. So let's go on to the next example. And this is the first time that we're going to be talking about pseudocode in this class. So since I think all of you or almost all of you are computer science majors, you're probably familiar with what I mean by pseudocode. But if you're not, pseudocode is essentially the same thing as computer code that you might be writing, but instead of using a specific language like Java or C or Python, pseudocode is computer code written out in English, I guess you'd say. So for this course, instead of using a particular language, most of the time we're going to be using pseudocode because you might not all know the same computer language, or at least I can't assume that you all know a particular one. Let's see, I'm going to box this over here just for clarity. Okay, so I'm using P again for a propositional function. And since I'm using a computer, I can't use an infinite set, like the set of all numbers. A computer can't handle infinite numbers of things. So my domain is going to be this smaller set with n things in it that I've labeled D1, D2, D3, up through Dn. And I've written, or actually the textbook author wrote this little bit of pseudocode. It says that for I equals 1 to n, if the negation of the proposition is true, then the program here is going to return a false. If none of these statements are true, if the negation of the proposition P of di is never, if this is never true, then instead of ever returning a false statement, it's going to get through this whole, what do we call this, a control flow sequence or something like that. it's going to get through all of it and then just get to this line and return true from the program. Can anyone tell what this little snippet of program does? What's the purpose of this? So no, it's not going to return the value P of D. So remember that value is either true or false. The value of this is either true or false. But it's actually going to be looking at all of the values for the proposition. Because of this for loop, we're going to start at I equals 1. We're going to take this value, plug it into the proposition, or plug it into the propositional function, excuse me, and then put a negation on it. Doesn't it just cancel the negation? So remember and you might not know this, the program is going to stop if it ever actually runs one of these return statements. So the function ends, or the program, let's say, ends. So it ends after a return statement is actually executed. So if what's going to happen here is if you plug one of these into your proposition and your proposition is false, you're going to add a negation on it, and that's going to make your proposition, this whole proposition in parentheses, true, but this is false. So adding a negation to a false proposition makes it true. And that's the case where it's going to return false from the program. It's going to return false if this value, the truth value of P of DI, is ever false. And if this is always a true statement, if the proposition P of DI is always true, then this little snippet of code is never going to be executed. It's just going to skip through all of this and return true at the end, if all of these values are true. Okay, yeah, it can be hard to type out these complex kinds of ideas. So let me tell you what it does if you haven't worked it out for yourself. So what it's going to do is it's going to tell you if this proposition for all x, P of x is true or false. Because if P of x is always true, this is going to be false all the time. So it's going to skip this and return true. If a single one of these values is ever false, then this if statement becomes true. That means this line is going to be run, and the program is going to return false. So I think I should switch my screen over. Somewhere that I can actually run a little bit of code. So I'm running Python. This isn't pseudocode anymore. So instead of saying for I equals 1 to n, I have to say something like for oops, I left off a letter. For I in the range 1 to n plus 1. If you don't know exactly why I have to write it that way, that's fine. This course isn't about Python. It's about it's more of a math course. Okay. Let's see. So I should add a comment up here. So my P of X is going to be, in this case, the statement. Let's just do X is greater than 1. And the domain of this course is just going to be the set of numbers 1, 2, 3, up to n, just to keep things simple. So if not, since I'm allowed to use that negation in Python, if not X is greater than 1, then my program should return false. Oops, can't spell. And we need a capital F. And then otherwise, we're going to return true. So before I run this program, should this return true or false after I run it? Is my statement for all X in this domain, X is greater than 1, is that a true statement or a false statement?
False.
It's false, because this first number, 1, is of course equal to 1. So that makes this false. So let's run it. Let's see. I guess I haven't set this up quite right. I didn't actually set it up as a function. I should have written this before class, of course. Let me stop the screen share while I fix that. Okay. Oops. There we go. Need to fix my syntax here. There we go. And then we need to run the function. But you can see that there's a problem here. I didn't define the value of n. And of course, the computer needs to know that before we can run it. So let's just pick the number 10. And like I said, should have fixed all of these mistakes. Okay, someone is writing on the screen. I did not know that was possible. Let's see. So first of all, I'm curious how you're doing that. And then second of all, try not to do anything that distracts from the rest of the class. Oh, there is an annotate button up here. Ah, interesting. I think that's new. Okay, so now that we actually have the right syntax, the function does return what we expect it to be. It's false because it's false for the first value. But if I replace my less than symbol with the less than or equal to symbol, then we know that this is always going to be true, even for that first value. So if we change that slightly and run it again, then the function returns a true value. So this is what the pseudocode does. This is the Python version of the pseudocode. And you could replace this little bit of text that I've highlighted with any kind of propositional function that you can think of, as long as you know how to program it. Let's see. Right, the best part of coding is debugging. Yeah, I just should have done that before class instead of live. Okay, so that's how the pseudocode might look if you actually programmed it. And whenever I do programming, whenever I do coding examples, I'm always going to be using Python because it's, I think, the simplest language to read, even if you don't really know how to program in Python. You can probably read a Python program if you know anything about programming. Okay, any questions before we move on? Okay, so let's take a look at this next universally quantified statement. This one says for every real number x, if x is greater than 1, then x plus 1 is greater than 1. So what do you think? Is this a true proposition or a false proposition? So it is a true proposition, which it should be since I'm asking you to verify it. But we need to be a little bit careful with this one because here our domain of discourse is the set of all real numbers. And what I'm saying is that I can plug in any real number here into this proposition or into the sentence to make it a proposition. Okay, so if I plug in, well, I guess we should break it down into two parts. If x is greater than 1, if the number I'm plugging in is actually greater than 1, what happens? Well, this is definitely true. Right? If you plug in the number 2 or 1.5, if you add 1, then you're definitely going to get something bigger than 1. But what would it mean to plug in all of the other numbers if x is less than or equal to 1? Is this still a true statement? Well, we have to be a bit careful here because the propositional function, the thing that I'm plugging x into, is actually a conditional statement. So the proposition, if x is greater than 1, then x plus 1 is greater than 1, has a false hypothesis. This part's false. What do we know about conditional propositions when the hypothesis is false?
The if statement must be true for the then statement. Or the then statement has, hold on, how do I say it?
If the first part is false.
Yeah, then the second part can be true or false.
Right.
But if the first part is true, the second part has to be true.
Right. So when x is greater than 1, we can definitely say that the second part, x plus 1 is greater than 1, is true. But if this part is false, if the hypothesis is false, then it actually doesn't matter what the truth value of this part of the proposition is. So this makes the conditional vacuously true. So even though the hypothesis is false, the conditional statement is still true. So overall, this universally quantified statement is true. And it doesn't matter what happens when the hypothesis is false, because it's vacuously true. Okay, any questions? No? Okay. So that looks like our stopping point for today. Next time we're going to talk about the other kind of quantified statement that we haven't gotten to. So I will see you guys on Friday afternoon.